on cryptocurrency. End sequence as a consensus enforced relative time lock. Since the activation of BIP68, new consensus rules apply for any transaction containing an input whose end sequence value is less than 231. Bit 1 less than 31 is not set. Programmatically, that means that if the most significant bit 1 less than 31 is not set, it is a flag that means relative lock time. Otherwise, bit 1 less than 31 is set. The end sequence value is reserved for other uses such as enabling check, lock time, verify. End lock time, opt-in replaced by fee, and other future developments. Transaction inputs with end sequence values less than 231 are interpreted as having a relative time lock. Such a transaction is only valid once that input has aged by the relative time lock amount. For example, a transaction with one input with an end sequence relative time lock of 30 blocks is only valid when at least 30 blocks have lapsed from the time the UTXO referenced in the input was mined. Since end sequence is a per input field, a transaction may contain any number of time-locked inputs, all of which have sufficiently aged for the transaction to be valid. A transaction can include both time-locked inputs, end sequence less than 231, and inputs without a relative time lock sequence greater than equals 231. The end sequence valid is specified in either blocks or seconds, but in a slightly different format than we saw used in end lock time. A type flag is used to differentiate between values counting blocks and values counting time in seconds. The flag time is set in the 23rd less significant bit, i.e. value 1 less than 22. If the type flag is set, then the end sequence value is interpreted as a multiple of 512 seconds. If the type flag is not set, the end sequence value is interpreted as a number of blocks. When interpreting end sequence as a relative time lock, only the 16 least significant bits are considered. Once the flag bits 32 and 23 are evaluated, the end sequence value is usually masked with a 16-bit mask, e.g. end sequence and 0x0000FF. Figure 7.1 shows the binary layout of the end sequence value as defined by BIP68. 31 disable flag, 22 type flag, 15 value 0. Figure 7.1 BIP68 definition of end sequence encoding, source BIP68. Relative time locks based on consensus enforcement of the end sequence value are defined in BIP68. The standard is defined in BIP68 relative lock time using consensus enforced sequence numbers. Relative time locks with CSV. Just like CLTV and end lock time, there is a script OP code for relative time locks that leverages the end sequence value in scripts. That OP code is check sequence verify, commonly referred to as CSV for short. The CSV OP code, when evaluated in a UTXO's redeem script, allows spending only in a transaction whose input end sequence value is greater than or equal to the CSV parameter. Essentially, this restricts spending the UTXO until a certain number of blocks or seconds have elapsed relative to the time the UTXO was mined. As with CLTV, the value in CSV must match the format in the corresponding end sequence value. If CSV is specified in terms of blocks, then so must end sequence. If CSV is specified in terms of seconds, then so must end sequence. Relative time locks with CSV are especially useful when several chained transactions are created and signed but not propagated. When they're kept off chain, a child transaction cannot be used until the parent transaction has been propagated, mined, and aged by the time specified in the relative time lock. Median time passed. As part of the activation of relative time locks, there was also a change in the way time is calculated for time locks, both absolute and relative. In Bitcoin, there is a subtle but very significant difference between wall time and consensus time. Bitcoin is a decentralized network, which means that each participant has his or her own perspective of time. Events on the network do not occur instantaneously everywhere. Network latency must be factored into the perspective of each node. Eventually, everything is synchronized to create a common ledger. Bitcoin reaches consensus every 10 minutes about the state of the ledger as it existed in the past. The time stamps set in block headers are set by the miners. There is a certain degree of latitude allowed by the consensus rules to account for differences in clock accuracy between decentralized nodes. However, this creates an unfortunate incentive for miners to lie about the time in a block so as to earn extra fees by including time-locked transactions that are not yet mature. See the following section for more information. To remove the incentive to lie and strengthen the security of time locks, a BIP was proposed and activated at the same time as the BIPs for relative time locks. This is BIP 113, which defines a new consensus measurement of time called median time passed. Median time passed is calculated by taking the timestamps of the last 11 blocks and finding the median. That median time then becomes consensus time and is used for all time lock calculations. By taking the midpoint from approximately 2 hours in the past, the influence of any one block's timestamp is reduced. By incorporating 11 blocks, no single miner can influence the timestamps in order to gain fees from transactions with a time lock that hasn't yet matured. Median time passed changes the implementation of calculations for end lock time, CLTV, end sequence, and CSV. The consensus time calculated by median time passed is always approximately 1 hour behind wall clock time. If you create time lock transactions You should account for it when estimating the desired value to encode in nlock time, nsequence, CLTV and CSV. Median time passed is specified in BIP 113. Timelock defense against fee snipping. Fee sniping is a theoretical attack scenario where miners attempt to rewrite past blocks, snipe higher fee transactions from future blocks to maximize their profitability. For example, let's say the highest block in existence is block hash 100,000. If instead of attempting to mine block hash 100,001 to extend the chain, some miners attempt to remine hash 100 hash 100-000. These miners can choose to include any valid transaction that hasn't been mined yet in their candidate block hash 100,000. They don't have to remine the block with the same transactions. In fact, they have the incentive to select the most profitable, highest fee per KB transactions to include in their block. They can include any transaction that were in the old block hash 100,000 as well as any transactions from the current mempool. Essentially, they have the option to pull transactions from the present into the rewritten past when they recreate block hash 100,000. Today this attack is not very lucrative because block reward is much higher than total fees per block, but at some point in the future transaction fees will be the majority of the reward or even the entirety of the reward. At the same time, this scenario becomes inevitable. To prevent fee sniping, when Bitcoin Core creates transaction, it uses nlock time to limit them to the next block. By default, in our scenario, Bitcoin Core would set nlock time to 100/001 and on any transaction it created. Under normal circumstances, this nlock time has no effect. The transactions could only be included in block hash 100/001 anyway. It's the next block, but under a blockchain fork attack, the miners would not be able to pull high fee transactions from the mempool because all those transactions would be time-locked to block hash 100/001. They can only remine hash 100/000 with whatever transactions were valid at time, essentially gaining no new fees. To achieve this, Bitcoin Core sets the nlock time on all new transactions to current block hash +1 greater than, and sets the n sequence on all inputs to 0xFFFFFFE to enable nlock time. So I'm going to here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.